All right, guys, welcome back. So what we're going to do now is talk about another way to estimate. So you just estimated with rectangles. Trapezoids actually turn out to be an even better way to estimate an area. So again, let's look back at the same area. Let's split it up at 4 and at 8. So what we're going to do with a trapezoid is we're going to use the height at both endpoints. So instead of just using the height at one side or the other, we're going to use the height at both sides of our intervals. We're going to go up to the function 0, we're going to go up to the function 4, and then draw a straight line between those two. From 4 to 8, we're going to take the value of the function 4 and the value of 8 and draw a straight line between those two. Now, as you can see, this area certainly is not perfect, but it looks pretty good. It's actually pretty close. And this does turn out to be better than Riemann sums in almost all cases. But the area of a trapezoid is a formula that you've probably forgotten. So if you have a trapezoid that looks like this, that has just one base here, and then it has some height on one side and then some height on the other side. The way you find that area actually is you could do 1/2 times base and then height 1 plus height 2. So you kind of take the average of the heights and then multiply it by the base. You might remember a slightly different formula from geometry if this was turned sideways, but this will work fine in this case. So in our conveyance, it's going to be 1/2 times the base times the height at the left endpoint plus the height at the right endpoint. Okay, so let's use the same table and estimate this integral using a trapezoidal sum. So what we're going to do again, let's think of the intervals. So the intervals here again are 0 to 3, 3 to 5, 5 to 6, and 6 to 10. So of course here the base is 3, the base is 2, the base is 1, and the base is 4. So what we're going to do is we're going to set up this formula for each individual interval. So as we go from 0 to 3, we have 1/2 times 3 times f of 0 plus f of 3. As we go from 3 to 5, we have a base of 2, and then we use the height of both of them, 3 and 5. Okay, and then as we go from 5 to 6, we have a base of 1, and then we use the height at 5 plus the height at 6. Okay, and then from 6 to 10, we have a base of 4, and then we use the height at 6 plus the height at 10. So within each interval, we're using the height on both. So you might notice, right, that like some of these values show up in twice. In fact, all the intermediate values are used in the intervals on both sides. Okay, now there's some simplifying we can do, right? 1/2 times 2 is 1, that just cancels. And then we'll just get these values out of the table, right? So what this turns out to be, I'm going to use this space. So this is like 3/2 times... Okay, actually, I'll just use the whole space down here. We'll do the next problem later. So this is 3/2 times, and then for 0 to 3, I use the height of both. So that's 5 plus 7. As we go from 3 to 5, the 1/2 and the 2 cancel, so that's just 7 plus 3. As we go from 5 to 6, we have 1/2 times 1, so it's 1/2. And then those values that we got there are 3 and 2. And then 6 to 10, 1/2 times 4 is 2 times 2 plus -1. Now, you could get a number for this, but who cares? This is fine. Like, you don't need to, like, spend time working it out. You know the idea. When you write these problems up on my test, on the AP test, show this work. Show you're finding the intervals. Show you're getting the heights in both intervals. That's going to help you get as much partial credit as possible. So, but that's what we're doing, right? We're using the height on both endpoints. So same thing here. If I give you this problem right here, and we'll solve it down below, same thing, right? I'm going to think about the intervals. So I'm going to go, I have this function x squared minus 3. So if I'm going -1 to 5, that has a width of 6. So I'm going from -1 to 2, and then I'm going from 2 to 5 for each interval. So each of these have a base of 3 because it told me to use 2 trapezoids of equal width. So here we'll do 1/2 times 3, and then f of -1 plus f of 2. And then 2 to 5, we have 1/2 times 3, and then f of 2 plus f of 5. And again, like you could just find these values, right? We can say, looking at this, right, f of 5 is 5 squared minus 3 is 22. F of 2, 2 squared minus 3 is 1. F of -1 is 1 minus 3 is -2. And then those are the values that you would plug in and get a number for this. So I guess we could do that. So that's like 3/2 times, okay, so -1 and 2. So that's -2 plus 1, and that's 3/2 times 1 plus 20 deucer. So that'll turn out to be 3/2 times -1, so -3/2. Oh, geez, plus 3/2 times 23, and you can see why I didn't want to finish the problem. Okay, That's negative 3 plus 69 is 66 over 2, which is 33. Okay, but the important part again is the setup, right? Actually computing this is like a 7th grade thing or whatever. Getting to this step and getting the right values, setting up the intervals correctly, that's the focus on all these problems. Okay, the only thing else I wanted to talk to you about is a trapezoid an over or under estimate? So in this case, what you do is you check concavity. Because as you can see, if you are concave up, if you try and just draw a couple trapezoids here and find those areas, you'll see that it overestimates, right? It overcounts. If it's concave up, those trapezoids turn out to be an overestimate. So if it was increasing, decreasing, that told us if a left or right sum was an overestimate or underestimate. If it's a second derivative, we care about concavity. If it's concave down, the opposite's true, right? If we have a concave down function, if we draw a couple trapezoids here, we can see it's going to be an underestimate, right? It misses this area right above. Okay, so that's trapezoids. Again, make sure you know this setup, the 1/2 base times height 1 plus height 2. Bring me questions in class. I'll see you guys soon.